Hello, everyone. My name is Xiaodi. I am a PhD student in Australia National University. I am presenting the work of our ICAPS 24 paper, a counterexample-based approach to probabilistic conformance planning. This work was supervised by Grastien and Charles Gretton. You can contact us by using email, and I listed email address here. Let's start from background. Probabilistic conformance planning is also called PCP. A PCP problem is a planning task where either initial state is unknown or action effects are unknown. Uncertainty is quantified using discrete probability distributions. A solution is also called a plan, must achieve goal with probability above threshold. A plan is a sequence of actions. Our work only focuses on the problem with unknown initial state. This is an example of PCP problem. A robot is in a 3x3 grid, and we don't know where the robot is. The robot has 4 actions, left, right, up, and down. When robot moves into the wall, there is no effect. The initial state's probability distribution is labeled on the grid. And you can compute the probability of each initial state by using product rule. To make our problem be more interesting, we say robots can move left and right only when the robot is at the top line. The goal state is at x2, y2, and we set the probability threshold theta as 0.6. A valid plan is up, up, right, left, and down. The reason is that this plan satisfies 6 initial states, and the total probability of these 6 initial states is 0.8, which is greater than 0.6. The reason why PCP problems are hard to be solved is that you see in this example, there are only 9 initial states, but the number of combinations of initial states is 511, which means the planner should consider 511 cases before find a plan. To make the problem be easier be solved, we are doing domain projection. The context of a subgoal is the set of facts in the subgoal alongside the facts that depends on transitively. We are using the context to do the domain projection. Let's see how we are doing the context. In the action up, there are 2 conditional effects, and we say that y1 depends on y2 and y2 depends on y2. y2 depends on y3 and y3 depends on y3. After we draw the dependency graph, we put all the facts in the graph into a set, and we got the first context, which is about y. The same, if we are looking at action right, we can draw the graph about x, and we have the context about x. The tag of an initial state I is the intersection of I with context C. For example, we have 2 contexts, and if we consider initial state x3, y3, we can get 2 tags. The first tag comes from the intersection between context 1 and the initial state, which gives us x3. The second tag is from the context 2 intersect with initial state, and we get y3. In this running example, we totally have 2 contexts and 6 tags. From the first context, we can do the domain projection, and we have a projected domain 1. From the second context, we have projected domain 2. On both projected domains, it has projected goal. Each tag in projected problem represents a set of initial states. For example, in projected domain 1, x1 is a tag, and it represents 3 initial states, which are x1, y1, x1, y2, and x1, y3. After doing domain projection, 9 initial states are represented by 6 tags, so which means our planner doesn't need to consider 511 cases, but fewer cases need to be considered. The domain projection increases the efficiency of searching counterexamples. So I will define what is counterexample later. Now let's introduce our algorithm. We name our algorithm as probabilistic captchas. Our algorithm is in rounds. It generates candidates plan and looks for counterexamples. A counterexample is an initial state that the candidate plan does not satisfy. Our algorithm works until success probability exceeds a predefined threshold theta. If no candidate plan exists in a round, the algorithm will stop because the problem is proven unsolvable. If goal state threshold is theta, the total probability of counterexamples in each round should be greater than 1 minus theta. Instead of searching counterexamples, we are searching counter tags. A counter tag is a tag that all initial states it represents are counterexamples. Our algorithm is proved to be sound and complete. This is an example of our algorithm. In the first round, candidate plan is none. And the meaning of candidate plan is none is that the robot is always standing at the initial location. So there are 4 counter tags, x1, x3, y1, y3. Here we pick up y3 as counter tag in the first round. In the second round, we update candidate plan. See, if the robot stands at y3, after doing the new candidate plan, the robot finally moves to y2, which is the goal state in the projected domain 2. So the new candidate plan satisfies y3. Based on the new candidate plan, we can find 2 counter tags, which are x1 and x3. The reason is that if robot initially stands at x1, after doing up, up, and down, the robot still stands at x1. But in the projected domain 1, x2 is the goal state. So x1 is the counter tag. x3 is also the counter tag. Because our algorithm incrementally searches for the candidate plan, so we only ask candidate plan satisfies 1 tag in each round. So you see our new candidate plan is up, up, right, down, and this candidate plan satisfies y3 and x1, not x1 and x3 here, only x1, because we only ask the candidate plan satisfies 1 tag in each round. The reason here is that some problem, maybe some initial states are unsolvable. We have to avoid that unsolvable initial states. So here we only ask the plan satisfies 1 tag in each round. After we do many, many rounds, we can meet 2 cases. The first case, there are not enough counter tags, which means the last candidate plan is a valid solution. The second case, no candidate plan can be found, so which means this problem has no solution. These are the technical details of how we compute candidate plan. We first remove the precondition of each action. For example, in action right, it has precondition y1. We remove it, and we add a new conditional effect. And this conditional effect says that if robot is not at y1, that's invalid. So even though we don't have precondition, but the new conditional effect makes sure that the plan must be a valid plan. And the second thing is we add the interpretation number after each predicate. Say if we have 3 interpretation numbers and then there are 3 robots, they initially stand as 3 different locations, but they are doing the same action, they execute the same plan. Okay, I will explain it later. So we are still using the round example, and in round 2, we have 2 counter tag sets. The first one is y3, the second one is x1, x3. Okay, because we have 3 tags here, so that we have 3 interpretation numbers. you can regard it, there are three robots. The first robot stands at Y3, the second robot at X1, the third robot stands at X3. And our goal states, if you remember that in the second round, we only ask the candidate's plan satisfies one of counter tags. So here you see first robot, you should go to the goal state, but the second robot and the third robot, one of you should move to the goal state. So here you see I use the disjunctive goal for interpretation 2 and interpretation 3. Now let's introduce how we compute the probability of counter tags. If we simply sum up the probability of counter tags, the probability is wrong. The reason is that some counter tags, they may have overlapped in initial states. So we have to delete the probability of overlapped initial states. But this is very complex, right? So we have to find a simpler way to compute the probability. We are using DDNF. The reason is that using DDNF to compute the probability is only linear time complexity. So let's see how we do it. We first introduce chance variables, A, B, C, and D. And we write some formulas. And you see like X1 or not A, not X1 or A. And these two formulas guarantees that the tag X1 always has the probability of 0.2. And say if we want to compute the probability of X1, X3 or Y1, we should write this formula. And we put all of them together into a DDNF compiler, and the compiler would return as a graph like this. And we use the algorithm here to compute the probability from the leaf node to the root node. And we finally got the number 0.6. So which means the probability of Y1 or X3 is 0.6. Okay, now let's verify it. If we compute the probability for each initial state and sum up these 5 initial states, and we can see that the probability is 0.6 as well. So which means yes, the DDNF is a correct way. We further improve our algorithm by using hitting set strategy. Go back to our round example. If you still remember in round 2, we have disjunctive goal here. In our experience, classical planners find problem without disjunctive goals relatively easy to solve. So here we are using hitting set strategy to help classical planners select which sub-goal to achieve, and we can avoid disjunctive goals. For example, here we have 2 hitting sets, 1, 2, and 1, 3. So we have 2 options. The first one, achieve 1, 2. The second one, achieve 1, 3. And so that we can say, hey, classical planner, you just need to solve the first one. And the first one is conjunctive goal. And classical planner solve it very, very fast. Okay, let's see our experimental results. Our algorithm is powerful when probability threshold is high. So you can see in the first table, the bound with the probability threshold 0.99, it takes 4.85 seconds. But when the probability threshold is 0.75, it times out. The reason here is that when probability threshold is low, in each round, we have to find many counter tags. So that's our disjunctive goal is very long, and it's hard for classical planners to find a plan with such long disjunctive goals, right? The second one, hitting set strategy makes our algorithm become much more powerful, especially when theta is low. Okay, compared with the first table, the second table still bound question with 0.75 probability threshold. It takes 6.7 seconds to find the plan. You see, we avoid disjunctive goal, and classical planner would be much faster. Compared with our algorithm, other PCP planners such as Probabilistic FF and Pound, they are powerful when probability threshold is low. The reason here is that if probability threshold is low, normally the plan length is short, and they are searching the plan from initial state to goal state using like the graph. And if the plan length is short, they just search, so they can search fewer nodes. If the probability threshold is high, they have to search more nodes so that they are powerful when probability threshold is low. This is all the presentation of our work. We welcome everyone to contact us to discuss the PCP problems or other problems, or even counterexample-based approaches to solving any planning problems. I listed the email address of authors, and you can contact any of us. Thank you very much.